So welcome everyone to our STAMPS webinar series. It's a pleasure to introduce Collin Politsch from Carnegie Mellon University. So Collin is currently a postdoctoral fellow in the machine learning department at Carnegie Mellon. He received his joint PhD in statistics and machine learning from CMU on the topic of statistical astrophysics, on research spanning extrasolar planets to the large-scale structure of the universe. So Collin's research interests include applications of statistical machine learning methods to problems in astrophysics, spatial temporal data analysis, uncertainty quantification, and forecasting COVID-19. So Collin has done some really interesting work on mapping the three-dimensional universe using intergalactic absorption data. And we're very fortunate to have Collin here today to talk about some of that work. So Collin, maybe you can take it from here and share your screen.
There we go. Can everybody see that?
Yes.
Good. Okay. Thank you. Oh, thank you, Anne, for the introduction. I'm very happy to be here to talk about this work. As Anne said, this is work that I've been working on for a very long time on three-dimensional mapping the universe via the Lyman alpha forest, more specifically mapping the intergalactic medium. And let me just parse this title because I know we have a very interdisciplinary audience here. And so three-dimensional cosmography just means three-dimensional mapping the universe. The high redshift universe means the very distant universe, or analogously the early universe, and using intergalactic absorption means that I'm going to be using spectroscopy here and analyzing the absorption features in the spectra of high redshift objects. Feel free to follow me on Twitter. I tweet about science, among other things. I'm not sure if they're here today. Here are my three collaborators on all of this work and the entirety of pretty much everything I've worked on in astrostatistics. I get to call them collaborators now as of June, but of course, these were my three PhD advisors, Larry and Jesse and Rupert. Oops. Okay, so this talk is largely derivative of my thesis defense, which was in June, and so I will not be offended if you attended my thesis defense in June. This is going to be very similar, so I would not be offended if you sign off now. No worries there. But I kept this slide in here in particular, the overview of all the work that I did in astrostatistics over the 6 years my 6 years at Carnegie Mellon as a PhD student, primarily because Larry Wasserman and I have two ADA projects in the statistics department for the current first years. And so the intergalactic medium via the Lyman alpha forest is what I'm going to be talking about today. And that's what I mainly focused on during my PhD research. And I studied a variety of other problems in astrostatistics to a slightly lesser degree than the intergalactic medium. But we have a couple ADA projects that the exoplanets via the transit method and spectroscopic classification and redshift estimation that we're very excited about. We'd like to have a first year pick up an ADA project and run with us on that. And so feel free to shoot us an email there. You can read a little bit more about these things in chapters 2 and 3 of my thesis, which is currently embargoed as of right now because of the topic of today's talk. And so I should take that opportunity to say, please don't redistribute any of the materials, the pictures, the three-dimensional map or anything like that. Because yeah, it's currently under press embargo until it passes peer review, but you can find these 4 applications and our 2 papers published earlier this year in monthly notices of the Royal Astronomical Society. Today, I'm going to be talking about the intergalactic medium map via the Lyman alpha forest. Okay, so this is kind of how I've structured this talk. I'm going to start with a little bit of background on the Lyman alpha forest. The astrophysicists on the line, if you're most likely familiar with the Lyman alpha forest and the Sloan Digital Sky Survey, feel free to stand up and go to your kitchen and grab a cup of coffee, whatever you wish for the next few slides, and then come back. This is mostly for the statisticians and the other people on the line that aren't familiar with these things. And then right up front, I'm going to give you a summary of the work very high level summary of the results. And then in the second and third parts of the talk, I'm going to take a deeper dive into how exactly we made this map of the intergalactic medium, starting out with one-dimensional mapping the intergalactic medium along quasar observer lines of sight, so one-dimensional mapping, and then extending that to three-dimensional mapping the intergalactic medium, given the given the densely sampled catalog of quasars given by the Sloan Digital Sky Survey has allowed us over the past few years to map the intergalactic medium in 3 dimensions. So I'll talk, and this is going to be the focus of today's talk. I'm going to talk about the 3-dimensional spatial model. Spatial modeling is very expensive, and we're mapping a very, very large volume of the universe. So we're going to rely on some distributed computing here. I'm going to talk about optimality because I'm a statistician, and likewise, I'm going to talk about uncertainty quantification. And then kind of our first order science that we do with this map is to catalog statistically significant candidates for galaxy protoclusters and cosmic voids in the matter distribution. Okay, getting started here with the Sloan Digital Sky Survey. The survey that's been ongoing for over 20 years now. I'm going to show you a video here of the 3-dimensional distribution of galaxies. This redshift survey that's been mapped by the Sloan Digital Sky Survey. So we are here at the center of this, our observable universe here. And at the high redshift end, we have these quasars, very luminous objects that have active supermassive black holes at their center. And so because they're so luminous, they can be seen at greater radial distances. And then as you get closer here, it's easier to see these low redshift galaxies. And so we can really get a high number density of them and see the structure of the matter distribution of the universe. And so I'm pausing here to emphasize for a second that you can resolve the cosmic web at these low redshifts. You can see kind of these nodes of the cosmic web that are galaxy protoclusters or galaxy superclusters. And then you can see kind of these less dense regions, kind of where there's more black. You can call those cosmic voids. And then the web, the spider web-like structure are filaments of the cosmic web. But the focus of this talk is the Lyman alpha forest, and so it's a feature in the spectra of high redshift quasars. The quasars are out here, the white objects, some of the more distant yellow objects. And so the question here is, can we do more? Can we do more than map this point process of the matter distribution of the universe? And the answer, as I gave away in my abstract and in the introduction, is of course yes. So on the left here, this is an overview of the matter distribution of the universe. We have galaxies, which I just showed you, mapped by the Sloan Digital Sky Survey. In the middle here, we have the intergalactic medium. And so this is what's traced by the Lyman alpha forest, which I'm going to get into a little bit more background detail in a minute in the next couple slides. And then on the right, we have the dark matter distribution. So all of these things very closely, because of gravitation, very closely trace one another. Galaxies have already been mapped by redshift surveys. The problem attacked in this work is mapping the intergalactic medium. And so that's the focus here. We're not directly mapping the dark matter distribution. That's more the realm of gravitational lensing, but because of the close interplay of these two forms of matter, you can basically take the map of the intergalactic medium as a proxy for the total matter distribution. And consequently, when you map the intergalactic medium, you can use it as a sort of proxy to infer that the high density regions of the intergalactic medium, it can be taken as candidates for galaxy protoclusters or filaments, and then the low density regions are going to trace cosmic voids. And this is a hydro simulation by Renyu Chen and Jeremiah Ostreicher from Princeton. Okay, so how do we observe the intergalactic medium? What's our observable here? There's this broad kind of subfield known as absorption spectroscopy, which is not unique to astronomy by any means. But the way I define it here is just a set of spectroscopic techniques that measure the absorption of light as a function of wavelength due to some interaction with a medium. And so when we look up in the sky here, this is taken from the Sloan Digital Sky Survey website. The top two plots are just some photometry, and so we see this very faint light source in the sky at some particular celestial coordinates, and we zoom in on it here. A priori, really, we have no idea what this is. We have some techniques for figuring that out, though. In this particular case, we use spectroscopy, and so gathering a spectrum of this light source here, we look at this, and this is by an astronomer's eye, this is pretty obviously a quasar, and this kind of gets into one of the ADA projects. Again, just taking a side note here to advertise to the first years, when we see a light source in the sky and we gather its spectrum, we want to be able to classify that object, say whether it's a star, it's a galaxy, it's a quasar, and how far away it is. And so we're kind of just taking that for granted right now, that this source right here is a quasar, and it's estimated to be at redshift 2.39, which is just a proxy for its radial distance from Earth. Okay, but the thing to pay attention to for the sake of this work is these kind of sharp absorption patterns over here. This is what's called the Lyman alpha forest. This is the Lyman alpha spectral line right here, and we have these absorptions over here that are due to foreground neutral hydrogen absorption in the intergalactic medium. And so the intergalactic medium is a gas composed of elements, primarily hydrogen in its neutral state, and that's exactly what this Lyman alpha forest is tracing here. So zooming in here, I'm showing you a simulated version of this spectrum zoomed in on the Lyman alpha forest, just to kind of underscore this point. What's happening here is we have this idealized spectrum. The orange dashed line is it's called the continuum radiation of the quasar. It's the spectrum of the quasar when the light first left it before it interacted with any medium. And so it's a very smooth spectrum. And then it's on its way to Earth. There are these absorption patterns that occur along the line of sight due to intergalactic hydrogen absorbing the light. And so given suitable statistical methods, we can invert these absorptions to obtain a one-dimensional density map of the hydrogen along this one-dimensional line of sight. And the hydrogen, as the most abundant element, can serve as a suitable proxy for the total matter distribution. Okay, wait a second here. So just to kind of walk through this again in pseudo real time. This is there's a lot of things going on in this video animation here. What's happening is we have a quasar here at the far left. We have quasar light leaving it and traveling through intergalactic space along its one-dimensional line of sight to Earth. And we have these what look like clouds here, which are just overdense regions of the intergalactic medium. And we'll see what happens to the spectrum of the quasar. So as it travels through this medium and it transects these clouds, we get these absorptions in the intergalactic medium. There's lots of things going on in this plot. What I want you to focus on is just this spectral line right here in the forest that's created from the intergalactic hydrogen. There's other interesting things going on over here, but the most important things right here, and we're just going to ignore these. Feel free to talk to me offline about other things of interest. So the bottom line is we get this forest, and we want to use statistical methods to invert the forest into a density map of the intergalactic medium. Okay, so the Baryonum Oscillation Spectroscopic Survey was a sub-survey of the Sloan Digital Sky Survey that operated in from 2008 to 2014, and is the most prolific Lyman alpha quasar survey. And so this is where our data comes from. So I'm showing you kind of, again, the point process of the universe based on the Sloan Digital Sky Survey. I showed you the video earlier. Now I'm showing you a two-dimensional cross-section of it. And so Boss quasars, here are the high redshift quasars, the very bright ones that we can observe from very far away, Boss galaxies. Lower redshift here. And then here's a nice animation from the Sloan Digital Sky Survey. that underscores exactly what it is that we've mapped in this work. At low redshifts, at low radial distances, we have this point process distribution of the galaxies. At high redshifts, the Lyman alpha forest makes this gaseous medium accessible to us, where we can use these distant quasars and their foreground absorptions to reconstruct this three-dimensional distribution of intergalactic gas. And that's exactly what we've done in this work, for the first time. Based on our analysis, there are approximately 160,000 usable Lyman alpha quasar spectra, these distant quasars, in order to make this three-dimensional map. Okay, so now we're through the background. I'm going to give you the high-level summary of the work before I get into the details. So the high-level summary here is we have these quasars that are at distant radial distances, and we don't have anything in between here because the Lyman alpha forest is in the ultraviolet wavelength range. And something that I should have mentioned prior is cosmological redshift. And so these wavelengths, as this light travels through space, are being stretched. And so a consequence of cosmological redshift is that we can't observe the Lyman alpha forest with ground-based spectrographs at redshifts below about redshift 2. And so this is basically unobservable to us in the intergalactic medium. So we take all of these, what we call Lyman alpha quasars from the Sloan Digital Sky Survey. The first step here is to infer the density map along these one-dimensional quasar lines of sight. And so that's what I'm showing you on the right here. We take each of these quasars and we make a one-dimensional map of the IGM. A little bit of lag between my slide transitions, I apologize. Step 2 is to pool the sight lines, to take all of these sight lines together and infer a three-dimensional map of the intergalactic medium from all of the one-dimensional maps together. Again, we're very statistically rigorous people, and so the step 3 is to quantify the total statistical uncertainty in the full three-dimensional map. Step 4 is to use that uncertainty quantification framework and our reconstructed map, to identify statistically significant overdensities and underdensities in the intergalactic medium that we can then catalog as candidates for galaxy protoclusters and cosmic voids. Okay, now that's the summary of the work, summary of the results. Up front is that here we have the largest volume, large scale structure map of the universe to date. And I'll get to what exactly I mean by the largest volume, large scale structure map. I need to define that. But what we're seeing on the left is approximately 1/1000th of the volume of the intergalactic medium map that we've created. Lyman alpha flux contrast is our pseudo observable variable here. And so the low values of Lyman alpha flux contrast correspond to overdensities in the cosmological matter distribution. And then the high values correspond to underdensities. And so in red, we have the overdensities, blue, we have the underdensities. So we might see something like dark red like this and think, okay, that's a candidate for a galaxy protocluster, and then something in deep blue is a candidate for a cosmic void. Here we have a two-dimensional cross-section of the three-dimensional map, and so we really get a sense of the depth of the map. It spans redshift 1.98 to 3.15, and then at low redshifts we get the galaxy distribution observed by the Sloan Digital Sky Survey. So just some logistical summaries of the map. It's 47 gigaparsecs, okay, slide transitions are a little bit wonky today, I apologize. 47 cubic gigaparsecs over h cubed. And so assuming a value for the Hubble constant based on the measurements from the Planck CMB, that's approximately 154 cubic gigaparsecs. As far as the sky coverage, approximately 10,300 square degree footprint, which is about 1/4 of the sky. I'll show you another cross section of the map that gives you a better sense of the sky coverage here in a moment. As I said before, spans the redshift range 1.98 to 3.15. And using our map and our uncertainty quantification together, we're able to catalog approximately 180,000 candidates, high significance candidates for galaxy protoclusters and voids. And this is really an unprecedented number for these two high redshift types of structures. So that's what I mean when I say the largest large-scale structure map ever made, is that we can actually resolve these two types of large-scale structures over large volumes. Okay, and altogether, the computational cost of this, again, as I alluded to earlier, the expense of spatial modeling is extreme, and we made a number of serious precautions and approximations in order to make this possible at all. But the total cost of this is approximately 3 million distributed CPU hours, 342 distributed CPU years. And so this is fully distributed computing. This is not multi-threaded, this is not multi-core, this is very memory intensive computing. And so each machine is configured with approximately 200 gigabytes of RAM. And so each of these units of time is one machine running with 200 gigabytes of RAM. Okay, here is the sky coverage projection. As I mentioned before, this is effectively the sky coverage of the Sloan Digital Sky Survey's 12th data release. And so we have the northern galactic cap over here, the galactic plane of the Milky Way, and then the southern galactic cap. And just kind of zooming in here again to underscore this point, we have red regions signifying overdensities in the universe and blue regions signifying underdensities in the universe. And this is at redshift 2.1, so one specific radial distance from Earth. Okay, I'll talk a little bit about one-dimensional mapping, the intergalactic medium. I'm not going to get into too much detail. This is in our published work, and I'm going to focus on three-dimensional mapping here. But one-dimensional mapping is an essential stepping stone in the three-dimensional mapping problem. So on the left here, again, I'm showing you a Chen and Ostraker simulation. We have quasars in the background here, and the light transecting the cosmic web in the intergalactic medium. We have the giving rise to the Lyman alpha forest on the right here. And so, okay, now we're going to start to finally formulate this as a statistical problem. We have our observable, the flux observed of each quasar along the line of sight. And for each of these spectra, we assume there's some signal here, and then plus some noise. Okay, and the signal can be factored into the continuum radiation times some flux transmission here. And so the continuum radiation, again, is this orange dashed line. And then the transmission is basically this photon transmission probability that it makes it through this particular point along the line of sight in this gaseous medium. Okay, and then once again, factoring here the transmission probability into an average transmission probability over the full sky. We're really interested in these fluctuations about the average cosmic flux contrast over the full sky, which serves as a proxy for the fluctuations about the average density of the universe over the sky. Okay, so defining flux contrast here is just, yeah, this transmission probability minus, it's a fractional quantity, the transmission probability minus the average transmission probability over the sky divided by the average transmission probability. Okay, and in our published work, again, we proposed this estimator that utilizes trend filtering. And so I'll get into that in a second. And I have some extra slides in case anyone's curious. But basically, in our published work, we proposed this estimator that given an observed spectrum, first you denoise the spectrum with a nonlinear smoother. In this case, we use trend filtering. You minus this estimator m hat, where m is defined as the product of these two quantities. So basically a continuum that passes right through the Lyman alpha forest. A mean, a very smooth mean is much easier to estimate than a very smooth maximum. And so that's the idea there. and then divided by that smooth mean again. Okay, so this is an illustration of a simulated spectrum of exactly this one-dimensional mapping method. Given a one-dimensional Lyman alpha forest, first we denoise it with this orange nonlinear estimator, which is trend filtering. And then we take a low S estimator, very smooth, and the bandwidth's optimized based on simulated data. If you want, you can ask me for details later. And then you take the ratio of these two things and you subtract 1. And in my thesis and these published papers, we show that this is a very good estimator, trend filtering. The canonical reference is Ryan Tibshirani, 2014. So based on this plot, you can see that, at least in this case, it appears to be a very good estimator of the Lyman alpha flux contrast. So again, I want to underscore this point that low values of Lyman alpha flux contrast correspond to supposed overdensities in the universe. In this case, we're looking at a simulation, and so this is indeed an overdensity in the universe, and the orange is our estimator of that Lyman alpha flux contrast along the one-dimensional line of sight. Okay, and Politsch et al. 2020 A and B, we go into trend filtering in detail and in the context of astronomy. It was kind of the first appearance of trend filtering in astronomy. Okay, but the question, of course, as statisticians is uncertainty quantification. We proposed an estimator here for the one-dimensional Lyman alpha flux contrast. What about the uncertainty in that estimator? So we propose a parametric bootstrap for this in order to gain these variability bands. And the idea here is to construct these bootstrap samples of these Lyman alpha forests. So for each Lyman alpha forest, we construct a bootstrap sample by taking the trend filtering estimator, the denoised version of the Lyman alpha forest, and add this noise distribution, which is assumed to be normal with some estimated variance, which I'm generally very skeptical of assumptions, but this is something that's actually, normality here is a pretty valid assumption has been well vetted by the Sloan Digital Sky Survey, and based on many exposures, these sigma hats are pretty well known. Okay, and then fit the trend filtering estimate to the bootstrap sample, define the Lyman alpha flux contrast, the bootstrap Lyman alpha flux contrast exactly as we define the point estimate, and then construct 1 minus alpha percentile variability bands by taking the percentiles of the bootstrap distribution. Okay, so this is a slide I already showed, and so the effect of this is that we can not only provide a point estimate for this one-dimensional map here, we can actually provide variability bands here. And so again, drawing attention to these dips in the Lyman alpha flux contrast, we can now say with confidence that these dips do indeed correspond to statistically significant overdensities in the universe. Maybe that line of sight is passing over a filament in the cosmic web. Maybe it's transecting a galaxy protocluster, something like that. Okay, now getting it to the focus of the talk is the three-dimensional map of the intergalactic medium. So this is generally a problem that's referred to in the literature as Lyman alpha forest tomography. It's been around for quite a while. Most of the work has involved hydro simulations. And here I'm just going to kind of go through some of the objectives and essentials of Lyman alpha forest tomography. The main thing is to, of course, reconstruct a three-dimensional large-scale structure map from a dense collection of one-dimensional maps. So I'm showing you here on the left, this is real data observed by the Sloan Digital Sky Survey. You can take these to be a bunch of one-dimensional, densely sampled maps. And what you want to do is take all these one-dimensional maps together, pool them, put them into some three-dimensional model, and reconstruct the full large-scale structure field. This is pretty much as far as the Lyman alpha forest tomography literature goes. I've been working on this for a very long time, so I'm going to state a number of additional objectives, essentials here that we posit should be part of the Lyman alpha forest tomography problem. So we approach this as a non-parametric and data-driven modeling problem. And so in particular, we don't make any probabilistic assumptions on the underlying Lyman alpha flux contrast field. We're averse to that sort of those strict assumptions. Is something I'm not going to, especially since this is recorded talk, I'm not going to call out any particular literature, but we're averse to making probabilistic assumptions because in general they're not very reasonable. Instead, our approach is to optimize the map to be predictive of structure that lies in between the sightlines. And so I'll give you kind of a hint, foreshadowing here. What we're going to be doing is holding out sightlines later on when we're optimizing the map and seeing how well we predict the structure on those held out sightlines. Okay, so objective 3 here is that we allow our spatial model to be multi-resolution. And the thinking here is basically that the universe has various scales of structure, and so too should our statistical spatial model that we use to model it. Uncertainty quantification, I've referred to this many times. We're very careful about it in the one-dimensional problem, and likewise, we're very careful about it in the three-dimensional problem. And in order to really infer any important science from this three-dimensional map, you need to provide the associated uncertainties with it. Okay, computational efficiency and scalability. And so this has been one of the biggest issues, one of the biggest hurdles in Lyman alpha forest tomography over the past 20 years. Because like I said, the BOSS survey data has been available for 6 years now, and nobody's made a map of this magnitude or even close. Spatial modeling over these volumes is very prohibitive. It's very difficult. And so computational efficiency and scalability is a huge consideration that has to be thought about here. And so we exploit sparsity in these matrix operations that I'm going to go through the math here with you in a minute. We exploit a great deal of sparsity. And as I mentioned earlier, we utilize significant distributed computing. Okay, on the right here, I'm showing you the mean transverse line of sight separation. This is something that's important up front to realize, is that somewhere over here is us a long way away. And then these one-dimensional maps of the universe are gradually getting farther apart purely due to the spherical nature. But also quasars are getting fainter from our perspective and more difficult to observe. And so the average transverse line of separation of these one-dimensional maps is getting much, much coarser. And so the best we can possibly hope to do with a three-dimensional large-scale structure map is to map the structure at or above the transverse line of sight separation. Okay, so getting into the actual three-dimensional spatial model here, I'm just going to tell you up front exactly what the final spatial model that we utilized was. You can see my thesis, which is embargoed for approximately 60 more days for the other things that we tried. But for now, I'm just going to assure you that we tried many things, and this was the final product, the one that we decided was the most capable, the best for mapping the intergalactic medium. So we call this a multi-resolution spatial kernel ridge regression. Basically, what's going on here is we have this delta F hat here, which I'm using the hat because there's already been modeling that's been done. And so this is a vector that includes all of the one-dimensional maps from the quasars. And then we have a basis expansion here. And so phi is a regression matrix based on the compactly supported radial basis functions, and beta is a vector of their basis coefficients. We have some weighting matrix in the middle here, which I'm just gonna kind of hand wave, but it's the usual basic idea of down weighting observations due to their inverse variances, but also an extra little step there based on the variance of small scale structure, because we can't hope to map the intergalactic medium at full resolution. But yeah, feel free to ask me more about that later. So we have this trade-off between this weighted sum of squared errors, and on the right here, we have this penalty. And so this is a generalized ridge penalty here. L2 with this generalized ridge matrix D that's imposing spatial smoothness in the reconstructed process. And then the idea is to solve this generalized ridge problem, take the estimated basis coefficients, plug them into this multi-resolution basis expansion, and boom, there you get your reconstructed 3D map. Is it that easy? No, it's not that easy. I'll get to that in a second. But to give you some sort of idea here, here's an example of the multi-resolution basis that we utilize. This is a set of one-dimensional radial basis functions built up from Wendland polynomials. So here's an example of 3 radial basis functions built up dyadically. And then this spatial smoothness, this spatial smoothness that arises from the spatial penalty matrix D. And so for this particular example, this is a one-dimensional example over here. Here's a two-dimensional example of spatial smoothness being imposed on the reconstructed process. And so you have a coarse scale of resolution in this case, and then slightly finer scale, and then a finest scale here. And we allow the number of levels of resolution in the basis to vary in order to optimize predictive accuracy. Let me check just a sec how I'm doing on time. Okay. Okay, so returning to this multi-resolution generalized ridge penalty, let me just talk through this mysterious D a little bit here, maybe a little bit quickly so I can make sure I get to everything. We construct D as a block diagonal matrix where each block of the matrix corresponds to one of the levels of resolution in the spatial process. Within each of these levels of resolution, we have this differencing penalty which imposes the spatial smoothness, and then we have I as the identity matrix here, and then 2 hyperparameters that control, let's see, alpha controls within each level of resolution the range of the spatial dependence, and then gamma I within each level of the spatial process controls the total contribution of that level of resolution to the total spatial estimator. Okay, and we use first order fusion here, and so for a three-dimensional spatial model constructed on a regular grid of radial basis functions, each basis function has 6 first order neighbors, and so we weight each basis coefficients by 6 and then -1 for each of its neighbors. And so the idea here is that we're encouraging the coefficients of neighboring basis functions to be similar. Right, this is the expanded penalty, and it looks a little bit scary. I'm happy to talk through it in questions, but for sake of time, I think I'm gonna go ahead and just skip ahead here. Okay, now distributed computing. And so returning again to this cost functional, this is a generalized ridge problem. And so it's strictly convex and differentiable everywhere. Therefore, it has a closed form solution given by this right here. But does that mean it's easy? Are we good to go? Absolutely not. The size of this problem is pretty staggering, and the number of observations is approximately 72 million. The number of basis functions in order to map the intergalactic medium at about the level of the transverse separation of these sight lines is 40 to 50 million. So this is a truly massive and high dimensional problem, very difficult to actually get the solution. So we use a distributed approximation here. And the idea of this distributed approximation is to take advantage of this kind of this spatial penalty here, that it's never exactly 0 at any pairwise distance, just as a kind of artifact of the ridge regression. But beyond a certain radial distance, the spatial dependence of this process is trivial. So what this allows us to do is to partition the total 47 cubic gigaparsec over h cubed volume into a bunch of subsets and compute a bunch of local estimators. So here's a local basis coefficients with some buffer, where we're including a buffer to make sure that this montage of maps fits together seamlessly. And after we compute each of these local sets of coefficients, we plug them into the local basis expansion to obtain a local map over some subvolume, and then we piece it all together. This distributed estimator is a piece together in a piecewise fashion. And this is approximately, if I remember correctly, 1,700 submaps of the intergalactic medium, all pieced together is what yields our final map. Okay, so let's talk about model validation. I've introduced a number of hyperparameters of this model here. So I'm just gonna let eta here be our vector of hyperparameters. And as I've mentioned, in accordance with our objective to maximize the predictive accuracy of this map in between the sight lines, we split the set of quasars given by the BOSS survey, 85 to 15% for train and validation. And we train on 85% and then evaluate how well we're doing for each value of the hyperparameter vector. And then there's this kind of technical step here that's estimate the large scale density field along each one-dimensional map in the validation set. And effectively what we're doing there is degrading each of the one-dimensional maps in the validation set to be equal to the resolution of the transverse separation, because that's the best that we can hope to map in 3 dimensions. Great, and so then we get to the question of what loss function do we want to use? And so we're analyzing a density field here in a discrete high dimensional evaluation of this density field. And so we utilize the Kendall-Tau ranking distance here to see how we're doing. This looks a little bit technical here. This is, for people familiar, this is the number of discordant pairs between our prediction and the actual maps in the validation set. This is much, much easier to understand in terms of its alias, the bubble sort distance. And so effectively what we're doing here, let's see here, is we get our 3-dimensional map predictions for each value of the hyperparameter vector. And then we, on the right side here, we have the validation set degraded to the resolution of the transverse separation. And we count the number of pairwise swaps that the bubble sort algorithm makes in order to get the ordering of these held out quasar spectra. Okay, and then overall, a large number of hyperparameter vectors, we take the minimizer of that loss function. And then recalling again the transverse line of sight separation, kernel ridge regression is a design adaptive method in the sense that it'll be higher resolution, it'll be wigglier in areas in the spatial domain where there's more data, and it'll be smoother in areas of the spatial domain where data are more sparse. But in the radial direction, as we see here, there's very significant heterogeneity. And so in order to provide the spatial model with an extra boost of design adaptivity, we optimize the hyperparameter vector separately in these 3 redshift bins. Okay, and so here's the analytical formula for our 3-dimensional map. We have a sum over 3 redshift bins, and then within each of these 3 redshift bins, we have a partition for our distributed computing, indicator functions, just all of these submaps pieced together. So this is what gives us this map that I already showed you at the beginning. I'm showing you the mall-wide projection here at one specific redshift. Again, deep red, over densities in the universe, deep blue, under densities in the universe. Okay, so estimation, there we go, check. But we're statisticians. We want to do real science with this. The question, of course, is what's real? Let me take a look first at the point estimate reconstruction itself over a variety of redshifts, so different radial distances. So I'm showing you here the same sky cutout of the universe. I think it's 20 degrees by 20 degrees at redshift 2 through redshift 3. And again, in accordance with our objective of mapping the intergalactic medium at the highest resolution allowed by the transverse sightline separation, Recall again that as we get to higher redshifts, quasars get more sparse, becomes more difficult to, or impossible to map high resolution structure. So that's exactly what we see here. Approximately 2.2, the density of sightlines peaks. So we can see a high dimensional reconstruction. Redshift 3, the resolution is much coarser as expected. Okay, so getting back to uncertainty quantification, we want to know what's real. So this is simply an extension of the parametric bootstrap that we utilize for the one-dimensional map. So we start with the data generating process of each of the quasar Lyman alpha forests. We start exactly from the observational model because we want to include all of the statistical uncertainties that go into the modeling pipeline. So we sample a bootstrap Lyman alpha forest for each of the approximately 160,000 quasar Lyman alpha forests. Okay, and then for each spectrum, just the one-dimensional problem, we're doing it again. We use trend filtering to estimate the flux signal, and then low S to estimate the mean flux level. Take the ratio of those two, -1. We get the Lyman alpha flux contrast along each one-dimensional line of sight. That's exactly what I just said right there. And then we pool all of those approximately 160,000 lines of sight together to compute a full bootstrap three-dimensional reconstruction in our distributed fashion of the full 47 cubic gigaparsec spatial field. Okay, as I just said, we produce 50 bootstrap reconstructions of those. Ideally, of course, you know, as a statistician, I'd like to produce more, but I also wanted to graduate, and these things took a lot of time. But anyway, as a kind of a very nice, pleasant surprise of this bootstrap distribution, it was not expected to be the case at all, because as I said before, even though we're assuming a Gaussian noise distribution for each of the Lyman alpha forests along the one-dimensional lines of sight, we're then passing the Lyman alpha forest observations through a nonlinear smoother, which we then pool all the Lyman alpha forests together to compute a three-dimensional spatial field, which is a linear smoother, but the one-dimensional step is a nonlinear smoother. So it's not expected a priori that the sampling distribution of this three-dimensional model would maintain its Gaussianity, but it is very, very close to Gaussian, which is very convenient for us because then we can just record in our database the estimated point estimate Lyman alpha flux contrast and the standard errors associated with that Lyman alpha flux contrast. And just for observational reasons here, I'm showing you the standard errors at one particular radial distance from Earth, the Lyman alpha field. In the northern galactic cap, this is generally true over all redshifts, that the signal to noise is higher for the observations and the uncertainty is greater in the southern galactic cap. Okay, so sort of our first order science that we're doing with this map that we made over several years, took a long time to produce, but now we're kind of getting into the doing some science with it. As I alluded to earlier in the talk, we want to map these overdensities and underdensities. And so in particular, we define these level sets of the Lyman alpha, three-dimensional Lyman alpha contrast field, letting Gn be the set that is in standard errors below 0, where 0 is the cosmological mean. And so anything that's below 0 is considered an overdensity. And then letting Vn be the level set of the reconstructed field that's in standard errors above 0. What we can do here, my slide transitions will work, is not so since we're very statistically rigorous about this whole process, is not just produce this three-dimensional reconstruction, but we can actually analyze what's statistically significant within this reconstruction. And so we can look at things like this. And so these are the 6 sigma significant structures in this particular cubic volume here. And so we have these blue structures that are at least 6 standard errors with respect to all of the statistical errors that go on in the modeling process below below the average density in the universe, and then conversely, red being 6 standard errors above the average density in the universe. And we catalog all of those things as candidates, statistically significant candidates in red for galaxy protoclusters, and blue, statistically significant candidates for cosmic voids. Okay, I'm showing you an orthographic projection here at redshift 2.5 of these candidates, the signal noise ratio again being higher in the northern galactic cap, so we get more statistically significant detections in the northern galactic cap than the southern galactic cap. So this is basically what we're doing right now. We're finishing this up, and this is the last thing that we have to tie a bow on before we submit this work. And if I can get this table to appear, here we go. This is a rough census of all of these statistically significant cataloged candidates for galaxy protoclusters and cosmic voids in this intergalactic medium reconstruction. And so at least a 3 sigma level, we have approximately 180,000 of each of these types of structures, and then up to an 8 sigma level, we still have approximately 20,000 significant detections, which is a very unprecedented number of these structures at these redshifts. Okay, so this slide just emphasizes how much, we value open source science, and so dissemination of all the data products. This is something that we're also currently working on. All data products of this work are going to be disseminated, accessible via the Stat Department website at CMU, powered by the Pittsburgh supercomputer. There's already a partial web page up there if you want to check it out. Feel free to, it's still a work in progress. At the end of the day, what it's going to contain is a 6 terabyte SQL database that makes the full 47 cubic gigaparsec over H cubed map queryable at a 1 cubic megaparsec voxel resolution. And then let's see, downloadable HealPix sky maps. So all these 2-dimensional sky maps that I've been showing you, all of those are going to be available in FITS format for every 0.01 units in redshift space between 1.98 and 3.15. And then the full downloadable catalog of candidates for galaxy protoclusters and cosmic voids, as I just mentioned on the last slide, approximately 180,000 of those each at least a 3 sigma level. Okay, here's just some relevant references, the first 4 being from my PhD work. The first one here being the current work in progress. For anybody that may have joined late, this is something that was approved as an inquiry at Nature earlier this year. I've given a few talks on it now, and the request is always that please, this is subject to a press embargo. We'd like to wait to do any press until it's past peer review, and then we can pursue these things. So please don't redistribute any of the materials in this talk, the pictures of the map or anything like that. And yeah, other relevant references. And thank you. I'm happy to take questions now.
Yeah, thanks so much for presenting some fascinating work here. Yeah, any questions here? Otherwise, actually, Collin, I have a question here. It's actually about your multi-resolution basis. I think it was like slide 17, you use radial basis functions. So yep. Are these kind of like radial basis functions that are shifted and rescaled? Is that what it is? Like you show the grid, is it like a uniform grid, or do you do something different? And like when you say level, do you choose like a dyadic scale, or like what's a first level? Like in wavelets, it's often dyadic scale. Yeah,
it's exactly that.
Oh, it's exactly
that. Everything that you just said was correct. Yeah.
So it's quite, it's quite impressive actually. So yeah, so obviously it's not orthogonal. And is it, so you have like a uniform grid and you have a dyadic scale, and that's
Yep.
kind of your, oh, it's huge.
Yep.
I see. And then you do this sparse, the optimization is
Yeah.
That's computational.
Yeah, thank you. I should have mentioned that right here, that even though, so we have this closed form solution here, and we have these compactly supported radial basis functions. And so phi is a very sparse regression matrix. W is the diagonal weighting matrix. And so phi transpose W, phi is a very sparse matrix. And then D is the spatial penalty. And the spatial, this is a differencing penalty. And so I think it's the previous slide here. And so we have all of these 6s and -1s. That's encouraging spatial smoothness. We have this delta transpose delta, which creates a different matrix, but it's still incredibly sparse. And so altogether here, this gram matrix is very, very sparse, which allows us to solve this linear system very, very efficiently via sparse Cholesky decomposition. And so what I alluded to earlier in the talk, and again, thank you for reminding me, is that what makes this possible is, number one, sparsity, is that we can make all of these local maps in a very efficient fashion, and then distributed computing, which our approximation allows us to piece them all together.
And your radial basis function, there are like compact support, like, I don't know how you, right?
Yep.
Okay. Oh, interesting. Yeah, I should probably see if the audience has questions. All right.
So I have actually one question, but I cannot use the raise hand as a host. So
yeah, it's okay. You can go ahead.
Let me jump in. Yeah, so I have so one question I want to ask is, so it seems to me that throughout here you assume Gaussianity, and specifically it was around slide 13 you showed those kind of trend filtered 1D line of sight fits, and it seemed to me that just by looking at those, it seemed to me that, you know, there might be some kind of skewness there. So yeah, these estimates here, these kind of delta Fs here that you have estimated, which then kind of go into your next stage fit. It seems to me that there are more of these kind of negative contributions than positive contributions. So it seems that it's skewed one way. But then the cost function you have for the 3D map effectively assumes Gaussianity because you have the least squares kind of data fit term there. So can you say anything about this? Would it make sense to try to account for, so first of all, is there a skewness issue, and would it make sense to try to account for that one way or the other?
Yeah, so that's a very good question. The Lyman alpha field is very non-Gaussian when you consider all the scales that go into it. And so the one-dimensional problem, we're able to map it along the line of sight in a much higher resolution. So that's exactly why we use a non-linear smoother here, why we use trend filtering, because we need it to be spatially adaptive in order to capture these sharp dips. We have, again, empirical results in my thesis and everything that show that trend filtering does better than linear smoothers, local polynomial kernels, smoothing splines, what have you. And then we have some coverage results for trend filtering in this parametric bootstrap in the thesis. But then getting to the second part of the question, which is the three-dimensional problem, on the large scales, so the large scales being the best scales, the best resolution that we can hope to map in 3 dimensions, given the BOSS survey, given our current observables, it is roughly, it's approximately a Gaussian random field. It's a spatially homogeneous process is what we would say statistically. And so it makes sense to use a linear smoother in this case. This is something that I've actually tested. Going forward, so this is an area that I'd like to, I don't want to ramble too much. This is an area that I'd like to continue to work in, and going forward with the DESI survey and everything, dark energy spectroscopic instruments, the next generation survey that's going to observe a lot more spectra of Lyman alpha quasars. We're going to be able to map the intergalactic medium at much higher resolution. And so we'll be able to reconstruct things like filaments, what we would call nonlinearities in the observed matter distribution. In that case, statistically, the optimal thing to do would be to have a spatially adaptive spatial model. And so something like a higher dimensional generalization of trend filtering. But for SDSS, for BOSS, the data that we currently had access to during my PhD, it makes sense to use a linear smoother, which you can think of as assuming Gaussianity.
Cool. Thank you.
I see Galen has a question.
Yeah, so my question is about how you talked about optimizing hyperparameters over different like 3 different sections of the redshift of the map that you have, right? Is there any guarantee, like, did you put guarantees in that the map will be smooth, like leading, like at those redshift boundaries, if that makes sense? Because I know you talked about enforcing smoothness between your different, like between the different subsets that you had the computational ability to fit. But is there any smoothness concern at those redshift boundaries that you imposed?
Yeah, that's a very good question. Thank you, Galen. So something that I omitted because I didn't want to get into too many technical details here is that there is a small post-processing step that we do after we evaluate the full 3-dimensional map on a Cartesian grid, is we pass a very narrow filter over it to make sure that we have smoothness at these particular redshift cross sections where we've used different hyperparameter vectors, and so that the full volume fits together seamlessly. But in general,
Thanks.
you're correct. There are small discontinuities. Yeah.
But that, I mean, it's not super, the discontinuities aren't super important still for finding these statistically significant high density and low density regions necessarily, are there?
No, they aren't. If any of my advisors were here today, but though, they would tell you that I'm like a little bit overly self-critical about these sorts of things, and I didn't like the idea that we'd have these kind of potentially we'd have these candidates for galaxy protoclusters and cosmic voids that might look a little funny, like they've been mosaiced a little bit. And so, yeah, wanted to do that little narrow filter just to make sure that everything looked smooth and cosmological.
Thanks.
Yeah, I have a question. So when you were talking to Mikael about going to higher resolution, do you mean higher resolution in Z, right, in depth? Because when it comes to the lines, the 1D lines correspond to the quasar spectra, right? So you're limited by 160,000, right?
Mm-hmm.
So higher resolution, you mean in Z, right?
Not just Z, just a higher resolution everywhere, really, because as we increase the number of quasar spectra, we're able to increase the resolution of the map at all redshifts.
Yeah. But so, how do you increase? I was just wondering, because at some point you were saying that the like 160,000 Lyman alpha quasar spectra, right? Those are the 1D lines, so you're limited by that in some sense, right?
Right.
So what do you mean we increase?
So DESI will.
Oh, okay, I see. Yeah, I see what you're saying. Just getting more data. Yeah, I see what you're saying. But you're not, are you thinking about, is that computational too difficult to change how you choose your basis functions? Does that matter?
It's going to be more, yeah, it's going to be more difficult for sure. There's going to be more basis functions. And then as we get in, as I already mentioned previously, instead of perhaps a spatial kernel ridge regression, this is part of my, I'm going to go ahead and plug, I'm on the job market right now, and I'm looking to continue work in Lyman alpha 4 tomography, hopefully at a DESI collaborating institution, so I can kind of lead this work, but it's going to transitioning from kernel ridge regression to a nonlinear method, which is statistically optimal for reconstructing things like filaments. The idea there is to go to an L1 penalized regression instead, which is going to require an optimization. And so instead of a closed form solution, we're going to have a more computationally expensive. So all of this was done on the Yale supercomputer, which should mention. And so it requires a supercomputer, but going forward, as we get to bigger and bigger data, DESI and beyond, there's further applications as well. 21 centimeter tomography, if that means anything to anyone, that's a direct application of this work as well. It's going to get more computationally challenging. And so every single computational consideration that we can make is important.